In topic two set theory, we start introducing quite a bit of vocabulary about different sets, how things can be rearranged, and some of the notation that goes along with it. When we create sets, we're effectively just kind of creating some sort of group. We can call this group anything. It'd be mathematical. It could be vowels. It could be animals that fly. Anything that has something in common. And this is really kind of rooted in logic and in things like programming and how things would be stored and categorized and Google searches. And there's a lot of applications and connections here to a lot of computing, for example. But we draw these sets and we want to ask a lot of questions and kind of just avoid some of the easy mistakes and just kind of follow some good logic when we kind of work through these different examples. Now, I just want a line. What's missing in this diagram for me is a nice border that goes around all of the information. A lot of the set diagrams that we're going to draw kind of have this. We use a lot of circles just to kind of make them stand out. I mean, the shape that you pick to conceal and group something together, I'm not going to be picky about that. But overall, we kind of want to contain it. And this is what we would, like right at the beginning, I would call this the universe. Universe kind of represents the entire, like the whole question, all of the things that we're trying to organize. In this case, it's the alphabet, the English alphabet. And there are only 26 things in this universe. You can count them up. There are absolutely only 26 things. Now, logically, I would probably call this the set V for vowels, and I would call this the set C for consonants, just to kind of give them some sort of context. Now, one of the fundamental rules of set theory and set notation and all the things, and in fact, a lot of this unit is kind of based around, and even when we move into counting methods and probability, is that we just can't count or draw the same thing, the same element. I'll even just keep my language as simple as I can. We can't count the same thing twice. Duplicates are essentially forbidden from now until you're done this course. We just don't want to count them. We don't want to count them as a probability. We don't want to count them as an outcome. And we don't want to count them as elements in these kind of diagrams. And it kind of forces us into, most of the scenarios that we're kind of going to work with. And the reason why there's an overlap in this diagram, it would be not very logical, not very precise, and definitely not very, mathematically precise if I drew the same thing twice, because sometimes y is a vowel, sometimes y is a consonant, and this would just be kind of a breakdown of the logic that we're trying to produce here. There is only one y in the alphabet, but it belongs to multiple sets. It could be categorized in both places depending on how it's used. And so we have this very, very special space, this overlap in the middle, or what we're going to call intersection. And not all Venn diagrams have overlaps, but a lot of them do. Creates more interesting questions. Because we can't draw the same thing twice, we're forced into this. Now, A, for example, is never a consonant, which is why it's very much defined in this space that we would call only a vowel. And, the letter Z is only a consonant, so it's not in the intersection. It is totally not within the V set. But anything that's within V, anything that's in C, is considered to be a part of that set. And that's what we would call this circle, this shape that we've used to contain all of the vowels. This is what we're we're kind of calling a set. You know, this is a set. And inside, we place little items in there that belong in that set. We're going to call these elements. And we want to make these really small calculations and just the logic behind organizing them. We're going to get you to organize different things. You have to figure out how these sets combine or if they don't combine. And we're going to start getting you to shade and make kind of logical calculations. Like the first thing that I could ask, based on that diagram up above, in notation n of v. You know, the number of elements in set V. It's kind of what we're asking here. And if you took a look at that diagram, would you say that there's only 5 elements? Because there's 5 things right here. Or would we also count Y? And we have to be there. There's no kind of vagueness. The set theory is just super. I mean, it is black and white. There is no gray area when we make little statements. The number of things that are in V are everything that's within this red V circle set. And if it's, even if it's in the overlap, it is definitely within V. We would have to make extra statements to say that it is in V, but not in C. We would have to go out of our way to get rid of things that are in that set. But there are definitely 6 elements in that set. If I asked how many things are in C, the number of elements in the consonant set, count them up, that looks like 21. There's the 20 that are only consonants plus the one that is sometimes a consonant, but in total, there's definitely 21. We're going to try and kind of lead you down these really, really seemingly kind of dangerous concepts like this. This is our first kind of logic puzzle of this little overview. What happens if I asked you to add the vowels to the consonants? Unfortunately, that just cannot be written. I mean, that's kind of what 6 plus 21 add up to. And I mean, there is some merit to saying that the answer is 27, but there's a couple of reasons why I would never agree with that. For one, the universe is 26. That's our 100%. There's no such thing in this universe beyond that. We're not going to create matter or create elements out of nothing. And so for one, there's just no way we can get beyond that universe, no matter what we added up. And going back to this fundamental rule, you can't count or draw the same thing twice. You cannot do this. And so because this answer included the Y twice, that is another reason why I would say that is poor logic. If you were to show a lot of work, you would have to say that, well, there's 6 in the N of V plus the 21 plus in the N of C, but we counted the Y twice, so it brings us back down to 26. And whether you kind of subtract 1 or whether you just take that into account when you're making your adding in the first place, it's kind of up to you how you organize yourself, because it's like a puzzle. You just have to kind of understand the rules of the game in order to make good decisions. And even though I'm getting you to add up all these things, I'm really just kind of, in theory, asking you to take the total of these sets. Now, sets can come in all shapes and sizes, and there's a bit of vocabulary that we kind of want to work with. So kind of right out of the gate, the kind of diagram that I had just drawn here is a very, very common scenario. I'd say a good percentage of the of the diagrams we're going to have to draw will include this little bit of overlap. And this is when the sets have an intersection. So I'll just say that these are very much intersecting. Now, there are very much sets out there that would not overlap, or else it would be kind of pointless to overlap. Like if I was just to say, even numbers, odd numbers. Is this space efficient? Is that space needed? Is it a waste of space? Is there a single number you could think that's both even and odd? And that's a tough ask. In fact, if you were to accidentally create space for something that does not exist, we're not really going to say that this is a wise way of using your diagram. It's very, very misleading. And we have a symbol in this unit that represents stuff that does not exist if you kind of accidentally draw it, or if it just doesn't exist somehow, and we would call that empty. And so this gets kind of way over the top and way kind of like not really necessary. So we would instead kind of avoid that unfortunate scenario. And if I was to create an even set of numbers, like the numbers 2, 4, 6, and if I was to create the odd set of numbers like 1, 3, and 5, I would have to draw them separate because that's logically what they are. They are totally exclusive. In this unit, there's a vocabulary we use that's called disjoint. And because we don't want empty space that does not exist and create this whole, very, very misleading scenario, there's just a lot of times when sets don't overlap. There's lots of things in life that are totally different from one another. There's no commonality. We call them disjoint, and their diagram would look like that. So, and going even further, we get into situations where you might have a large group, and within it, completely within it, not just intersecting, but completely within it, you have a smaller group within a group. If I think of things like, this is the big group of birds, and within the bird group, I could think of a type of bird. I could think of this as the group of owls. I mean, there are other types of birds other than owls. I mean, there's the woodpeckers, and then there's the cranes, and then there's the swans, and there's all these other little subsets, subgroupings, but owls would be completely within that group. And I mean, it would not make sense for me to draw it like this, because what owl exists that's not a bird? That would create something that does not exist. That would create an empty region, completely misleading. We don't need that. And I'll just move that back in because it is completely within the bird set. And this is kind of our scenario that we would kind of refer to as a subset. And there's a nice little symbol that goes with subset. Very, very much like the inequality, where we put smaller things on the small side and then larger things on the open side of that inequality symbol. We have a subset symbol, which is like a curved U. It's kind of like a U that's been pushed over. And I would have to say that the owls, I'll just call that set O, is a subset, that's our subset symbol, of the birds, where I've got my smaller owl set, my bigger bird set, and it's an owl as a subset of birds. And we kind of want to be able to kind of make those statements about subsets. Moving on. Created a scenario here where we would have to logically draw a couple of different things where we have to make a couple calls about what we're dealing with. Now, because these are like puzzles, we can use lots of puzzle-like strategies. process of elimination. For me, I would always start by drawing something disjoint. Let's see if this even works. Now, is there a number between these sets that is both a multiple of 5 and an odd number? And we're only dealing with the first 20 numbers. I've defined the universe as only 20 things, 20 elements. And I can quite quickly think of a number that's odd and an odd number. First of all, 5. 5 is a multiple of 5. 5 is odd. And then I would be in a real kind of a weird spot here of like, where am I supposed to write that? Am I supposed to write it in the first set? Am I supposed to write it in the other set? Am I supposed to write it in both sets? And I get myself in a pretty a not really nice scenario. So eliminated that possibility. There has to be a smarter way to do this. And so logically, I'm going to think of, well, maybe set A and set B share a little bit of things. I don't think there's subsets. I don't think all odd numbers are multiple of 5s or vice versa. I think that they are just intersecting sets within B. And I'll place in every one of the numbers between 1 and 20 in the correct place. 1 is odd, but not a multiple of 5. Now, where would the number 2 go, for example? Is it a multiple of 5? No. Bad choice. Is it odd? Nope. Bad choice. Is it both? Definitely not odd and a multiple of 5. So where would it go? We have this outside space. It's still within the universe. It's still a number in the universe, but it doesn't really belong in those specific sets that we have circles for. And so I would write the number 2 somewhere on the outside, just to kind of indicate that it's still a part of the question, but it's not within these sets. So I move on. 3 is odd. 4 is neither. 5 belongs in both because it is both a multiple of 5 and odd. 6, 7, 8, 9, 10. 10 is special because it is a multiple of 5, but it's not odd. It doesn't belong out in the universe. It belongs within that set called multiple of 5, but it's not in the joined intersecting space. 11 is odd. 12 is out in the middle. 13 is odd. 14 is out in the middle somewhere, or out and floating in the universe. 15 is a special number because it is both. 16, 17, that's not where 17 goes. 17, 18, 19, 20. Giving me a fully organized, logically accurate, efficient way to organize the numbers. And I decided that I was just going to organize them by odd. I just made up some random organization. Multiples of 5. And I created a set that has all the multiples of 5. I created the set that has all the odd numbers. And there was a little bit of leftover where none of those numbers are odd or a multiple of 5. And count them up, there are 20 things. And I could ask all sorts of questions here. I could ask, how many things are in A? How many things are in B? And then we start getting into the good ones. How many things are in A prime? This little tick is technically called the complement, but realistically means not. How many things are not in A? How many things are not in B? And then we can get into some special ones here, extra special. And I'll just use words here. How many things are in A and B? How many things are in A or B? Giving you a couple things to think about right off the get-go. Now, I mean, showing work is kind of nice in questions like this. And I'm a very visual person. I don't want to mess up that diagram up there. I'm going to draw a little mini diagram for each of these questions. And I'm going to shade. Come on. Give me my mini diagram. Ready. How many things are in A is technically asking you to take the total of all the things that are literally within A. And as I go to count, I see 1, 2, 3, 4. There was 2 of them in here. There was another 2 of them in here, if you count them up, and that gives me a total of 4. Number of things that were within B, well, that's the total of this segment of the diagram. All of the elements that are in B, which is 2 in that first segment, and then 8 in that other component of B. They were looking for the totality of B. They're not tailing to exclude any part of it. And that to me gives me a total of 10 elements in that segment to answer this question. How many things are not in A? This is where you have to be really careful. You know, these are the things that are within A. Therefore, logically speaking, we have to assume everything else answers this question. Not only are we going to accept the whole universe, because all that stuff is not in A, but we're also going to accept a little bit of set B, especially the part that's not in A. There's an entire huge amount of this diagram that is not within A. And that means I would be taking these 8 and 1, 2, 3, 4, 5, 6, 7, the other 8 that are on the outside, and I would get a grand total of 16 things are not in A. How many things are not in B? Same logic. I got to basically exclude B, but keep everything else to take this complement. The word not, B, complement of B, which means I'm only counting these 2 and these 8, and that gives me a total of 10, yet again. And we start introducing some words. And is going to be kind of connected to our, this is kind of our overlap word. I mean, there are different ways to use and or. If you're, say, writing an English sentence, if you're like, being in English over, analyzing a poem or something like that. But in math, and is very, very specific as a way of combining specific things, especially in sets. Set theory and computer programming use the word and in a very mathematically specific way. It regards when things are literally both true, which we call overlap, which we call intersection. This is also, going to be connected to an intersection of these sets. And that means I'm really only focusing on this segment where A and B Both are true, both are overlapping, and that was just those two. That was just those two in the middle. When we use the word and, we're going to be really, really specific, and we can get it really kind of take it in and really limit the answer to a very small region, which is completely opposite of the word or. The word or in mathematical sets is very much not limiting, but it's combining. This is the same thing as the plus symbol. This is the same thing as asking you to take the total of, especially if you don't add the same thing twice. I mean, we talked about this. Don't forget, you cannot count the stuff twice, but you still have to take the total. Where'd you go? Come back. Everything that's in A plus everything that's within B, which means I'm interested in all of this stuff. Some stuff was overlapped, yes, but we're just not going to count it twice. We just need to take the total of. We're going to talk about how this is called the union rather than an intersection. And it's either or. It's either, if A works, great. If B works, great. Take the total. And looking at my diagram, that means that I'm going to be taking 2 plus 8. This already is organized. I'm not counting the same thing twice when I have all these little mini totals. And that's going to give me a total of 12 when I take the union or the or of those sets. And topic 2 wants us to just get really familiar with a lot of vocabulary and being able to kind of use them and understand them in a logical way.